I'm John Trutte. I am COO of WSP Structures. I've been working for over 30 years. I started my career working for Van Wyk & Lowe, the current day Oricon. After that, I joined a company called Lillicrap Crutchfield. Lillicrap Crutchfield changed its name to LC Consulting, and I eventually became managing director of LC Consulting. And then we got ourselves acquisitioned by WSP. And so that's where I find myself today. I'm in charge of about 85 people, and we have offices on the structural side in Bryanston, Cape Town, and Durban. Yes, I've been asked to talk about failures or structural failures, and I thought I will kick that off by talking about why things go wrong structurally. And it's interesting, you can probably hypothesize about this a lot or be very theoretical, but if you've worked for over 30 years, things do go wrong, for sure. And you learn a lot about how to deal with failures and why they happen. So one very definite issue, and I see that happening quite often, is if engineers have too much work. And unfortunately, the way we operate, typically I see it's always too much or too little. And the too much, I think, is very dangerous for any engineer because things slip through. So too low fees, also dangerous. And I think one must always be very mindful of that, also from an insurance perspective, because if you accept fees that's too low and that do not allow you to do proper work and proper monitoring on sites, your insurance will frown upon that. So you have to be very careful about that. Apart from the fact that if you don't have enough fees, you can't pay a project proper attention. Continuity is an issue on projects. If you do a major project, you, as an engineer, study yourself into all the intricacies of that project. You know exactly what's done, what isn't done, where the critical things are, where not. And if you change an engineer on a project, you must be very careful because there's always gaps. I've been involved with the fixing up of a major project in Rosebank recently, and my belief is that the problem on that project was one engineer was in fact replaced by another, and certain gaps happened, and that's very dangerous. In fact, I feel so serious about that an engineer of mine recently decided to join somebody else. Don't know why, but he did, and I actually said I'd like him to take the project over from there. I'll look after the PI, but I want him to complete the project because I think it's just too dangerous that somebody else takes over a project that's in an advanced stage of completion. Inexperience is another major issue, especially in South Africa, where we have to train a lot of people. We must be very careful to allow inexperienced things to do critical designs. I mean, our field is you can make a mistake of 100% by just dividing by 2 or not doing it. So we have to be very, very careful about using inexperienced people. If we do, we must have proper systems in place to actually look after them and the designs they do. I always say that things go wrong or failures happen because of what we did not do, or the bit that we forgot to check, or the bit that we didn't design, or the bit that we never thought of. It's not typically what we did, it's what we did not do that typically goes wrong. And lastly, on that subject, I also believe there's a contractor I know quite well, and he always says you get 5 warnings. And I firmly believe you get 5 warnings. It may not be 5, it may be 3, but typically a problem doesn't just happen. There's a build-up to it. So you may do a design, and then somebody moves the columns further apart. Then somebody else comes and puts more load on top. Something goes wrong during construction, so they load extra extra stuff on the slab, but typically you get a number of warnings before it actually goes wrong, and the trick is to respond to that in time. When things go wrong, I believe there's a specific way to handle that. If you jump up and the first response is it my fault or not, you're not going to get anywhere, because then you get into legal wrangles or trying to protect yourself. Fair enough, you have to do that in any case, but I think one needs to separate the legal aspects or the guilt or who done it from how do we fix it. So the first step I normally have is to assess how big is the damage, so that we have an idea of what's the worst scenario. Okay, and typically you find it's not that bad once you've assessed that. And then from there you have to work on making the problem smaller, bit by bit. So you work at it and sort it out bit by bit. And then the who's to blame and whose fault it is must be a completely separate discussion. Because if you mix the two, you're not going to resolve either very quickly at all. Typical things that go wrong, I think the worst one and the most serious one is probably shear in slabs, where you have shear around columns. I think that's probably the most serious problem that you may have, because that can be an instant failure. It's typically extensive and can be absolutely catastrophic. So that's the big thing. I think when you check designs and when you check things on site, that's the area where you really have to focus to make certain, did I do that design correctly and did I check it properly? So that's probably the biggest single issue that can go wrong on a building. We do get things like settlement. I did a building in Parktown a few years ago. It's a garage. The rest of the whole complex of buildings we piled, and the garage actually was lower, and the geotechnical engineer advised us that we could put the garage on footings. Lo and behold, part of the garage then started settling. And we then had to underpin that. Fortunately, nothing cracked. The brickwork cracked. The concrete frame did not. I never realized how flexible concrete is, thanks heavens. But we fixed it that way. But settlement is something that happens a lot, so you really have to look after foundations, make certain you do that properly. Tolerances. It's not per se a catastrophic failure, but it's a failure from a serviceability perspective, where you have to be very careful about what tolerances you allow in a building, and everybody has a different approach to tolerances. Some people add all the tolerances together, others won't do that, but you have to be very careful about what tolerances you allow. Also, you may have a structural tolerance, that's fine, but when you get to finishes, the tolerances that you specified or allowed are too lenient for the finishers to cope with. So you have to be very careful about that. Deflection, same thing, where you have to be very careful about allowing too much deflection in a structure. So these are serviceability failures in a way. Movement of a building, so be very careful how you structure your movement joints, where you put them, how often you do movement joints, how they interface. I often see problems with that. You also get problems on parking decks with movement joints. They open up too wide, meaning the joints are too far apart, or maybe the structure doesn't quite suit the jointing, or very often I find the joint details are just not adequate for the work they have to do. Then time causes failure of buildings. I'm looking after, or did, after a building next to the double-decker highway in Johannesburg, and time has caused all the concrete to spoil off the reinforcing, and obviously a building like that now has a limited lifespan, and you need to deal with that. So time or maintenance can eventually create problems in buildings. How do we avoid these problems? We can possibly avoid that by checking designs. Now you can check designs in different ways. If you have an inexperienced engineer, you get a senior engineer to check. But you can go as far as getting an outside engineer to check your design, to audit your design. And we see more and more of that happening. I know some of the developers in the industry now do that as a rule, where they actually have an auditing company as well to go through designs. I don't think you can pick up every single thing that's wrong, because that means doubling up on the design, but you can certainly pick the critical elements. And we've done a number of design audits like that. And I think that's a very good approach. We also have to check things on site more carefully, I believe, than in the past. I find that the quality of construction on a whole, I think, has deteriorated. If I look at the quality of construction in places like Dubai, we really have a lot to answer for. And I believe that means we need more of a presence on site and double check how things are done on site, definitely in South Africa. You have to make certain that you have enough fees, as I said earlier, that you can actually visit site as often as you need to, because by now the fees have run out if you had low fees, and you need to make certain you have a proper schedule, that there's enough time to do the design properly and do your checks. So scheduling or programming of a project is very important. Engineers, I think, tend to very often play second fiddle to project managers, and I think that's highly dangerous. I do think the project manager need to lead the team. Nothing wrong with that, but I do think as an engineer you have a right and an obligation, if a program is too tight, to say so and get it changed to a program that's actually going to work for everybody. I think that's an absolute obligation. I thought I'll mention a few examples of things that have gone wrong in my career. I mentioned shear issues. We've done a design of a slab that had shear issues. I'm not going to say where it is, but if you ask me why did it go wrong, we had an inexperienced engineer, and I believe he wasn't properly checked. And maybe we didn't check it properly on site again. So it comes back to you get the 5 warnings. So if you did one of those things properly, maybe you wouldn't have had the problem. Settlement, I mentioned that earlier, the building that settled. That's happened on more than one occasion. Fortunately, could save this building. Of course, if you get very serious settlement, you're going to end up demolishing the building. We did a building in the middle of Sandton where we had full-time site monitoring responsibility. On top of the building, there were fiber-reinforced panels that hugged gutters on the edge of the building, and that was the design and supply item. And one day after the building was occupied, there's a smoker's balcony and people were standing on the balcony, and one of these panels came crashing down. Now, what that meant is the panel couldn't have been properly fixed. When we explored that, we found that the panels had a concealed fix. It was a design and supply, so our full-time site monitoring person, who was, I think, in his late 50s, early 60s, wasn't going to climb up to the top of the building to check that, and it went wrong. So we had to check every single panel and we eventually provided additional fixing to make certain the building is safe. So I think the problem there was site monitoring. If we site monitored that properly, we would have seen that the fixings were suspect. Well, we've recently finished a warehouse in Durban area, and we specified sheeting for the roof, and we took that down to on the sides, and the particular choice was made because this particular sheet has a very high rib, so it can accommodate a flatter roof, and therefore with a higher rib, more water. So it's very efficient from that perspective. Little did we know that this sheet has a propensity to what people in the industry call oil canning, so it creates a visual effect that may not be pleasing if it's not properly fixed, properly managed, properly supplied, properly manufactured. It ended up by the client asking that all the cladding be replaced. Now, it's very easy. I think what our engineer did is he looked in a catalogue, he saw examples of where this was used, which is exactly the application where we specified it for, and it didn't turn out very well. So I think the problem there is that you can get caught by what you did not check, because maybe you should have checked where was it installed, and actually maybe you should have gone and have a look. Now, how far you go obviously is tricky. I'm convinced there's very few, if any, engineers that go around town to actually check where similar sheets have been installed. Over the years, I've seen during construction where we use composite designs, where you have your sheet reinforcing over in concrete. Very often the way they pour the concrete, it all heaps up in one spot. Those sheets cannot carry those loads, and you then get a collapse of the sheet. I've seen that. People can get killed. I've also seen scaffolding collapse. Now, typically scaffolding and the design of scaffolding resorts with a contractor, but somebody still needs to design that and sign it off. And if scaffolding collapses and somebody's busy dealing with the concrete on top, that person typically gets sucked in through those holes and get killed. And I've seen that. So, trenches, that's maybe not structural, but in a way it has to stand, so maybe it is structural. Be very careful about trenches, especially trenches with water in, because your ground softens at the bottom and trenches do collapse. I've seen that. I've seen people being killed, and it's impossible to find somebody in a trench once it's collapsed. It is very, very serious. So I've walked on sites. If I see any deep trench and it's not properly dealt with, I will pull the people out of that trench immediately. I don't care if it's going to cost anybody money. And I think that's the crux, that we as engineers should not accept anything that's blatantly wrong. We should have the courage of our convictions and say so or stop a job, because you have the experience and the intellectual know-how to assess something better than anybody else, typically on a site. So you need to make a call when it's needed, I believe. When the World Trade, when Osama bin Laden and his mean men flew into the World Trade Center, I was called by Cape Talk, and that was the next day. And they asked me if I would be prepared to tell them why it collapsed. And I asked my secretary to go onto the internet and see whatever she could find about the structure of the World Trade Center, those two towers. And within an hour, I knew exactly what the design was like, how it was done, and I had a very good idea of why it collapsed. Now, these were tube structures. We call them tube structures because the stability is provided on the facade of the building. Where they had a Ferrandale facade, the engineers will know what I'm talking about. And in the middle there was a shaft, and the floors were, well, the shaft and the facade were connected to each other by means of little steel trusses, and then the floors resting on that. Now, obviously, what happened when the planes flew into the World Trade Center with all the burning fuel, the fire protection came off the steel trusses. In fact, they had it seen to about a year or two before. It came off and softened the steel. The steel then deflected and eventually collapsed. And then once one slab went, the whole thing concertinaed down. And I think what I read in that is that those buildings were absolutely efficiently designed. Absolutely efficiently designed. Look, typically what you do in a building like that, you design for redundancy, where you say, well, if I take a column out, will the building still stand? My belief is if those were concrete structures, those buildings would still be standing today. But they were steel structures, very efficient, and I don't know how much redundancy was designed into that. I'll need to speak to the designers about that. But also remember that maybe one should just, especially in South Africa, we're very apt to just design just so it's just enough. And I think that can at times be very dangerous. So you need to design for redundancy as well. Well, my take on that is that you're working against the forces of nature. So here you're working against gravity. And I think it's sometimes difficult to design against something you can't see. It's like an unknown enemy. But there's lots of technicalities involved in designing against gravity, of course. It does, yes. You have to be very careful about that. There's all these little rules for certain conditions. If you have a temperature, I think it's 5 degrees and dropping, then you can't cast concrete. And all those rules are made to, because it affects the process of hydration. So you need to be very careful about that. Typically, I find here in Johannesburg, we've had situations like that, but it's typically dealt with very carefully, or dealt with appropriately enough for Gauteng. And I must honestly say I've never had a failure because of temperature, never. Maybe I've been fortunate, but maybe our temperatures here are not that extreme, actually. I mean, in Dubai, it gets very hot, so that's another problem. But they would cool the water down, for instance, and then you get, in the colder regions of the world, they would use warm water. So they address it in different ways. I think as long as it's well understood, it's become such a complicated field that we typically actually talk to the concrete manufacturer, so to speak. What we typically would do, we'll specify the concrete strength and try to leave as much as possible of a detail to the designers of the concrete. So like the scaffolding, that's something that gets specifically designed to be tailor-made for what we need. I mean, we've been looking at a number of high-rise buildings in Sandton, and I know we specified concrete with 90 MPa strength, and I know we could get more if we wanted to. So things like that is quite possible. I don't think it leads to any more failures, but I do think engineers need to learn more about the possibilities that's now available as far as concrete is concerned. But it has become a highly specialized field, and I think it's best left with concrete designers. No. What green concrete really means is you add a certain amount of fly ash or extenders or replacement of cement, because cement's the baddie in all of this. And what that does to the concrete, it doesn't reduce the strength. It causes the concrete to take longer to get to full strength. And so the first port of call is if it's going to take longer and you have a slab that must be supported, it's going to cost you more money because you support it for longer. So there's a scaffolding cost. So you have to work that into your equation. Typically, I think you can make the concrete really green if it's lying on the ground, because it doesn't matter if it takes longer to get to proper strength. But structural slabs or slabs that's suspended, you really have it's a balancing act to say, well, we want it to be green, but we can't make it too green because it's going to take longer to set. And maybe that's something that's going to become more of an issue with time to come, because remember, in South Africa, we're right at the start of our green endeavor. But at this stage, no, I haven't seen any issues regarding that. I think we do have to watch out, because obviously we will all push the limits, like we've done in, I know we've done that with post-tension slabs, where post-tension slabs in the past used to be design and supply. What we now do is we do the design and then it gets supplied, because what happened is if you have all the design and supply people competing, these slabs get thinner all the time, and you may not remember, it's before you, but I remember that when I got onto the scene, a lot of these post-tension slabs were deflecting or cracking, were very alive, because they were just simply too thin, too optimally designed, and that created a lot of negative publicity around post-tension slabs. The same thing with trusses, where you have these serrated plates that hold the trusses together, and then these are also design and supply, and what you find is these trusses get thinner and the plates get smaller because it saves money. And we've in the past, I remember I eventually was called to go to a workshop where the industry was worried about trusses collapsing. And I've seen a lot of these things collapsing, and they collapse because they're just simply too marginally designed. So one must be very careful to not push the boundaries too far. And that's a word of warning to developers, in my opinion, that really want things to be as thin and as light as possible. That's all good and well, but you can get beyond a point where it's safe.
So badly?
I think it's a mixture of things. I think, as we just said, money is always an issue. I think if the money is tight, things must happen faster and quicker and cheaper. So your labour is cheaper, it goes quicker. You know, and simply what struggles at the end of the day? Quality does. So I think it definitely is a money issue. I do think it's a training issue as well. Now, we're lucky in a sense that South Africa still has relatively cheap labour, but obviously cheap labour also means that you're dealing with people with very little experience and know-how. So it's a two-edged sword. I believe we need to train everybody as much as possible and as quickly as possible in South Africa. And if that means we pay them more, well, hopefully we'll have better buildings. You see, in engineering, what we get in structural engineering, there's a lot of people, when they talk failure, they always think the building's going to collapse. Now, fair enough, that does happen. Buildings do collapse. They collapse in India, okay? We had that mall that collapsed in Bangladesh last year. So it does happen. It does happen. They had their 5 warnings, I can assure you, because I spoke to our contact in London who said, what you will find if you look at these buildings, there will be a design. Then when you go to site, the columns won't be that size. It will be smaller than what was designed. There will be less reinforcing in it. There will be an extra floor on top, which isn't part of the design. And then they will have a clothing factory there, and they'll put all the material on the top floor where it actually creates the most problems. So they have their 5 warnings. So if you had a badly built building, but you didn't do all these other things wrong, it would probably stand. Now the trick is with a building is, at what point do you get to, where's the tipping point? At one stage of my life I was involved with water purification design, the very first 2 years. And what I liked about that is the dirty water went in on the one end and clean water came out at the other end, and you knew it worked. But you don't know how well a building stands till it shows you something. In fact, a building has to move to work. So if you design a slab, it can only work, the reinforcing in that slab can only work if that slab deflects ever so little, but it has to deflect. If it doesn't move, it's not working. So it actually has to move to work. Now the trick is to control that movement or the extent, because that's why there's all these rules about you're allowed so much deflection, and that creates efficient slabs. So what you do as an engineer, you design that slab to get to that maximum deflection. Okay, it's slightly more complicated than this because you get instant deflection and then you get long-term deflection. Like when you have a plank over a trench with a brick on, if you go back a year later, that plank will have a permanent deformation. Now you get exactly the same in a concrete slab. So you get that's long-term deflection, and then you get the instant deflection. If you put the brick on, there's a little bit of a deflection immediately. And so we design for that. And the trick is to design that it actually gets to the maximum, because then you have an efficient slab. It goes wrong when the tolerances are wrong. So now it deflects too much, or the columns are out, so the slabs skew, and suddenly the skirtings don't work anymore, or the cupboard stand skew in the room. And that's the serviceability failure. And that's just as important. So if a building doesn't work, it stands. But if it deflects too much or moves too much, that's also a failure. I mean, if you do a tower block, these tower blocks, if they get very high, can deflect a meter, meter and a half. In fact, they can deflect much more than what people can accommodate from it's a bit like getting car sick. Okay, so some people will be more sensitive to that, others less, but people can't accommodate that movement because they feel uneasy about that. So you actually have to stiffen up the building to deal with that. Now, if you have a building that you're now a developer and the engineers designed this wonderful building, absolutely optimal design, but it deflects 2 meters at the top. You can't let it. That's a failure. You see? So you have to be very mindful of things like that. And that's serviceability failure.